So now that we have this connection between the integral and the derivative, between the area under a curve and the rate at which the curve changes, let's see how we can actually use that computationally. So let's look at y equals x squared, and let's just say we want to find the area under y equals x squared from 1 to 3. So we'd write that using integral notation. And we are looking to find this area that starts at 1 and ends at 3, and the bottom of which is defined by the x-axis, and the top of which is defined by the curve y equals x squared. So it's kind of something like that, trying to find this area right here. And depending on what the curve represents, this area might represent distance, or it might represent total amount of money, but in general it represents the total amount of whatever is changing here on this blue curve. Okay. So we do know that the area finding function is the antiderivative of x squared, or the integral of x squared. So now we just have to say to ourselves, what function, when you take its derivative, will give me x squared? What's the antiderivative? And this will be a little bit of a refresher of Calculus 1, but we'll get more of these rules in the next section, by the way. But think about 1/3 x cubed. Think about taking the derivative of that. If you took the derivative of that, the 3 would come down, multiply the 1/3 to give you 1. The derivative would just be plain old x squared. So it is true that 1/3 x cubed is the antiderivative, the integral, of x squared. So to work out the integral from 1 to 3 of x squared, I need this area finding function, 1/3 x cubed, and I need to plug, let's see, I feel like I want a different color now. I feel like I need to plug 3 in to tell me what the area under that curve would be all the way up to 3. And I also I need to take off the area before 1. So I'll subtract the area finding function, which is the integral, with 1 plugged in, with the lower limit plugged in. I'll switch back to blue just to keep this consistent. And I'll say right there, we also plug in 1. And we would then just crunch the numbers. So the rest of this shouldn't be hard for these particular numbers. Got 1/3, 3 cubed is 27, minus 1/3 and 1 cubed is 1. So 1/3 of 27 is 9, minus 1/3. So let's see, 9 is 27 thirds, minus 1/3 is 26 thirds. And that is the exact area under this particular function from 1 to 3. And this is a relatively straightforward example, but it all hinged on us being able to find this antiderivative, going from x squared to finding 1/3 x cubed. So let's look at another example. Let's see, let's maybe get rid of this one, and let's do one more. So let's try to find the area under, let's see, what should we do? Let's do cosine of x. And let's find the area underneath that from 0 to pi over 4. And I don't have a pre-made graph for this one, so let me just do a quick little by hand sketch. We know what cosine looks like as a function. It starts at 0, 1, so it starts here, and then it kind of goes down and back up, and this takes 2 pi to make a full cycle. So there's pi over 2 right there, and pi over 4 is about right there. And there's nothing wrong with using your graphing calculator, of course, to help you figure that out. But the area that we are trying to find looks about like this. We're trying to find this area under cosine from 0 to pi over 4. And we know to do that, we need to find the antiderivative of cosine. So some function that when you take its derivative, you get cosine. And I think if you remember your derivative rules, you'll probably remember what that function is. It is true that the derivative of sine of x is equal to cosine of x. So just a little reminder there. So when we are trying to find the area under cosine of x, we get that area finding function, which turns out to be sine. And again, I say I want to evaluate that by doing sine at the pi over 4. So that finds the total area up to pi over 4, and we want to subtract the sine at 0. So we want area all the way up to pi over 4 minus the area up to 0. And now again, it's just calculator work, or hopefully you know these values because you remember your trig. Sine of pi over 4 is square root of 2 over 2, and sine of 0 is 0. So this ends up being just square root of 2 over 2. And the book and the test too, when I have these problems on the test, I'll definitely want an exact answer. So you should know your trig functions. Your calculator will tell you that sine of pi over 4 is square root of 2 over 2. It'll tell you it's like 0.7 whatever. And I won't want the decimal. I will want the exact square root of 2 over 2 answer.